The phenomenon of aircraft heavier than air flying in the skies has multiple explanations developed by physicists, scientists, and mathematicians. But I do not intend to waste your valuable time in trying to explain why most of the widely known aerodynamic lift theories, including the equal transit time theory, are accepted by some but are challenged by others. I do not want to confuse you again by discussing those precepts that are with certain ambiguities, but instead draw your attention to a clean explanation that will give you a theoretically correct understanding about the generation of required forces to fly the aircraft through the clouds. Don's theory on aerodynamic lift, published in 2018, has touched upon the errors in some of the other theories in detail. The book is available in the Amazon bookstore if you are interested to do further reading on the subject. Just imagine a 560-ton, fully loaded A380 aircraft getting off the ground at a speed of 86 meters per second and continually climbing until it reaches around 35,000 feet. Whatever the phenomenon which lifts up this monster plane and takes it through the clouds to extreme heights and distances is a massive force. These forces are acted upon the aircraft's skin and transmitted to its internal structural members to prevent its collapse and deformations. By the control of the generated force vectors using control surface deflections and variable engine power, an aircraft could pitch, roll, yaw, and fly through the clouds to its destinations. As per the understanding of basic Newtonian laws of physics, the force is a product of an accelerating mass, or F equals ma. The only mass that outer surface area, or the skin of the forward-moving aircraft, comes into contact are air molecules. True to the statement, air molecules have a certain mass, though extremely small. Therefore, it is necessary to explain how these billions of tiny air molecules get accelerated to generate adequate forces to fly an aircraft. Don's theory on aerodynamic lift explains it all in detail using the three Newtonian laws. Let us refresh our memory about the three Newtonian laws for easy assimilation of the Don's theory. First law of Newton: every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. Second law of Newton: force equals mass times acceleration, or F equals ma. Third law of Newton: every action has an equal and opposite reaction. Don's theory on aerodynamic lift is an authoritative expression of the phenomenon of lift generation by aerofoil surfaces based on the three Newtonian laws governing the motion. Don's theory on aerodynamic lift: the vertical vector sum of centripetal forces induced due to the circular motion of air molecules in non-turbulent streamlines around convex and concave surfaces of an aerofoil is equal to the useful aerodynamic lift generated. In Don's theory, every phrase has either qualitative or quantitative reasoning, or both, and therefore, let's look at those phrases separately. Vertical vector sum, centripetal forces, induced, circular motion, air molecules, non-turbulent streamlines, around concave and convex surfaces of an aerofoil, equal to the useful aerodynamic lift generated. In the above phrases, circular motion, centripetal forces, convex and concave surfaces are completely new to the existing aerodynamic lift explanations. Let's go into detail and see how these billions of air molecules go into circular motion, following the contours of the convex and concave outer surfaces of an aircraft, generating centripetal forces. In an aircraft, while the wings produce a bulk of the positive lift force, its every surface produces either positive or negative lift, depending on its orientation to the relative airflow. We need to understand the dynamics of circular motion before discussing any further in order to fully comprehend the Don's theory. Acceleration in uniform circular motion. No object or mass is naturally inclined to travel on a circular path unless acted upon by an external force in accordance with the first law of Newton. Therefore, any object that travels on a circular path has to be continually acted upon by an external force in order for that object to remain in a circular orbit. However, its velocity is tangential to the center-seeking force, centripetal, which is changing the direction of the velocity of the object, continuously sustaining the circular motion. Even in uniform circular motion, the direction of the velocity changes continuously, which generates acceleration towards the center of the circle, even though the magnitude of the velocity is constant. Hence, the centripetal force, F sub c, equals ma sub c. This is the most important equation that helps us to quantify the magnitudes of forces developed by the airfoil shapes of aircraft, which are directly proportional with rotated air mass, related to density, square of the velocity of the aircraft, and inversely proportional to radii of its concave and convex surfaces, airfoil. Circular motion of air molecules about an aerofoil. A streamlined aerofoil moving through the medium of undisturbed air is continually pushing and pulling the air molecules into circular motion in the form of airstreams from their original state of equilibrium. In another perspective, it can be considered that the aerofoil is stationary, but the airstreams are fleeing past the aerofoil with a velocity equivalent to the indicated airspeed, or IAS, of the air vehicle. Airstreams made up of molecules that have a certain mass and are being deflected into circular motion from the original state of equilibrium forcefully by the convex and concave surfaces of the aerofoil. Aerofoils are designed in such a way, when they are moving through the medium of air, the surface contours either push or pull the airstreams into circular motion. These airstreams transfer from one circular contour to another in the form of an airstream bracing the surface as a boundary layer. Entry and exit of air molecules into circular motion with different radii. According to the theory, as soon as any mass exits the circular motion, it travels on a straight line unless acted upon by an external force, in accordance with the first law of Newton. Also, a mass that exits the circular motion by breaking away from the centripetal forces of a particular circle and travels on a straight line can transfer into a circular motion with a different radius if acted upon by centripetal forces of that different circle. In most aerofoils, when the air molecules exit the circular motion around a particular convex or concave surface, it enters another with a different radius and orientation. Therefore, air molecules that are speeding over the upper and lower surfaces of a wing profile in the form of airstreams rotate over a minimum of two different circular surface segments before they escape at the trailing edge. As depicted, the molecule A enters the circular motion with radius r sub 1, while the molecule B exits it and enters into circular motion with radius r sub 2. The molecule C completes the rotation around both convex and concave segments of the wing bottom and escapes at the trailing edge. Generation of centripetal forces. No mass will enter into circular motion if not acted upon by an external force. Convex and concave aerofoil surfaces of a forward-moving aircraft are forcibly inducing billions of tiny air molecules into circular motion without letting them stay static in their original state of equilibrium. As they rotate along circular contours, changing the direction continually, they are also accelerating towards the center of the convex or concave surface. These accelerating molecules that are having a certain mass are generating centripetal forces towards the center of the particular convex or concave they rotate around, obeying the second law of Newton. This center-seeking force is felt by the surface skin of the wing as an aerodynamic force obeying the third law of Newton. The radius of the convex or concave surface that air molecules rotate around is a critical parameter which has the highest influence on the magnitude of centripetal force generated through the rotation as the generated force F. The lift control devices of aircraft are controlling the radii of airstream rotation towards the trailing edge, augmenting the lift in many folds, which will be explained as we go along with this discussion. The radius of a curvature integrated to an aerodynamic profile was never a dimension considered for any lift computation in the past. Push and pull forces acting on the airstream. When the convex or concave surfaces are directly exposed to the upcoming airstream, those surfaces are forcibly pushing the air molecules into circular motion. On the contrary, when convex or concave surfaces are not directly exposed to the upcoming airstream, the Coanda effect is pulling the air molecules into a circular motion as depicted. Coanda effect explained. In accordance with the laws governing the circular motion, air molecules that leave the point D should be traveling on a straight line unless acted upon by an external force according to the first law of Newton. If it travels on a straight line, a vacuum has to be created between the airstream and the upper surface of the aerofoil after the point D. Since such a vacuum cannot exist in equilibrium, it sucks the aerofoil surface and the upper airstream together with an equal force. But in reality, the vacuum is never created. Before the vacuum is created, at angles of attack below 15 to 18 degrees, the airstream bends until it flows as a boundary layer along the convex DC arc with a radius r2, in accordance with the first law of Newton as depicted. The separation of the boundary layer after 15 to 18 degrees of angle of attack will be discussed in latter part of the video. Lift generated by Coanda effect. As the air molecules continuously taking a turn along the convex DC due to suction effect of the potential vacuum, they accelerate, generating centripetal forces towards the center of the convex with radius r2. The equal and opposite reaction, suction, felt on the arc DC is equal to the sum total of centripetal forces exerted on the air mass, or airstream, that curves along the surface DC. Therefore, the generated force due to the Coanda effect is felt as a suction on the aerofoil section DC instead of a pushing force. Factors influencing the generated lift. Now it is clearly evident that the magnitude of lift generated from an aircraft wing is directly proportional to the following: velocity of the aircraft, radii of the convex or concave surfaces incorporated into the wing, orientation of the convex or concave surfaces, mass of the rotated air volume, density dependent, angle of attack, or AOA. Velocity of the aircraft. Quantification of the lift can be done by direct application of the centripetal force equation of a rotating mass. In this quadratic equation, the generated force increases exponentially with the increase of velocity. Impact of changing the radii by lift control devices. The incorporated convex or concave surfaces of the aircraft wings are rotating the air masses, creating centripetal forces towards the center of each convex or concave, thereby producing the useful lift forces. In many convex and concave surfaces, radius is a permanent feature, but flaps, slats, and other lift control devices adjust the total radius and the surface area significantly, which result in increasing or decreasing the generated lift as depicted. In conventional explanations, the increased lift by control devices are attributed to the increased camber and the area of the wing. But in accordance with the Don's theory, increased lift is attributed primarily to the increment of the rotated air mass and decrease of the rotational radius. The deflected flap in the figure transfers the circular motion of the air molecules that were previously circulating over a concave surface area with radius r1 into circular motion with radius r sub 2. Also, r sub 1 is approximately 9 times r sub 2, and also the mass of the deflected airstream is higher with the extended flaps. This is the reason why the extension of flaps augments the lift considerably, enabling the reduction of aircraft velocity significantly during landing and takeoff. In this video, we discussed about 3 Newtonian laws, Dawn's theory on aerodynamic lift, theory of circular motion, acceleration in uniform circular motion of air molecules about an aerofoil. We will be discussing following topics in our next video: impact of convex or concave surfaces orientation, mass of the rotating air volume, angle of attack, or AOA, variation of the rotated air volume with AOA, change in surface area orientation relative to the AOA, quantification of lift force by the application of Dawn's theory.